Hello, everyone. Today we begin our study of time domain analysis for discrete time systems. In the process of learning the time domain analysis of discrete time systems, you can compare it with the time domain analysis methods you have already studied for continuous time systems. Comparative study can help you better master and understand both parts. To solve for the response of a discrete time linear time invariant LTI system in the time domain, we can generally use the iterative method, the classical method, or the convolution method. In the analysis methods for continuous time LTI systems, we also introduced the classical method and the convolution method. Before entering the main content of the course, let's first review the definition of the difference operation. The first concept, shifted sequences. Suppose there is a sequence. A sequence is a discrete time signal, f of k, then f of k plus 2, f of k plus 1, f of k minus 1, f of k minus 2, and so on are called shifted sequences of f of k. Second, difference operations. The first order forward difference, denoted by an upright triangle symbol, is defined as shown in the figure. The first order backward difference, denoted by an inverted triangle symbol, is defined for a sequence f of k as f of k minus f of k minus 1. We mainly use the backward difference, referred to simply as difference. The second order difference is defined as taking the difference of the first order difference. Once more, substituting into the formula, the first order difference of f of k equals f of k minus f of k minus 1, and the first order difference of f of k minus 1 equals f of k minus 1 minus f of k minus 2. Substituting yields the following expression. By analogy, the mth order difference is defined as f of k plus b1 f of k minus 1 up to bm f of k minus m. For a linear time invariant discrete time system, if the response signal is y of k and the input signal is f of k, then the nth order difference equation describing the input-output relationship of the system is as shown in the figure. Y of k plus a1 y of k minus 1 up to a and y of k minus n equals b0 f of k plus b1 f of k minus 1 up to bm f of k minus m. This can be written more concisely as the following expression. Here, a sub I and b sub j are constants and a sub 0 equals 1. The order of the equation is defined as the difference between the maximum and minimum subscripts of the response signal yk. The maximum subscript of yk is k and the minimum is k minus n. The difference is n, so it is an nth order difference equation. We can make a comparison. A discrete time LTI system is described by an nth order linear constant coefficient difference equation, while a continuous time LTI system is described by an nth order linear constant coefficient differential equation, as shown in the figure. The mathematical model of a discrete time LTI system is an nth order linear constant coefficient difference equation. The essence of a difference equation is a recursive algebraic equation. If the initial conditions and the excitation are known, the iterative method can be used to obtain its numerical solution. Given the initial conditions and the input, the system's output can be obtained by iterating the difference equation, as shown in the figure, with only y of k remaining on the left-hand side. Let us illustrate the iterative method with an example. Shift the difference equation so that only the y of k term remains on the left, and move 0.5 y of k minus 1 to the right-hand side of the equation. Substitute the initial condition y of negative 1 to obtain y of 0 equals 1.5. By analogy, we can obtain y of 1, y of 2, and so on. The iterative method for solving difference equations has a clear logic, is convenient for writing computer programs, and can yield the numerical solution of the equation. But it is not easy to obtain a closed-form analytical solution. We only need to have a basic understanding of it. Similar to the classical time-domain solution of differential equations, the complete solution of a difference equation consists of the homogeneous solution y sub h of k and the particular solution y sub p of k. The form of the homogeneous solution is determined by the characteristic roots of the homogeneous equation, and the form of the particular solution is determined by the form of the excitation signal on the right-hand side of the equation. This is exactly the same as for continuous time LTI systems. The homogeneous solution is the solution of the homogeneous difference equation, and its form is determined by the characteristic roots of the homogeneous equation. The form of the homogeneous solution falls into three cases. 1. When the characteristic roots are distinct real roots R1, R2, Rn, y sub h of k equals c1 r1 to the k plus c2 r2 to the k up to c n rn to the k. 2. When the characteristic roots are equal real roots R, y sub h of k equals c1 r to the k plus c2 k times r to the k up to c n k to the n minus 1 times r to the k. 3. When the characteristic roots are complex conjugate pairs. The form of y sub h of k is as shown in the figure. In these expressions, c sub I are undetermined coefficients, determined from the system's initial conditions. Next, we find the particular solution. The form of the particular solution is related to the form of the excitation signal. The particular solutions corresponding to commonly used excitation signals are shown in the table. Substitute the particular solution and the excitation signal into the original difference equation. Solve for the undetermined coefficients in the expression of the particular solution, and thus obtain the particular solution. Add the expression of the homogeneous solution with undetermined coefficients to the particular solution to obtain the complete solution. Using the known initial conditions, we can determine the undetermined coefficients in the homogeneous solution expression, thereby obtaining the complete solution of the difference equation. Let us illustrate the classical time-domain analysis method with an example. The problem gives the dynamic equation of a second-order linear time-invariant discrete time system, the initial conditions and the form of the input signal, and asks for the complete response of the system. Step 1. From the characteristic equation of the homogeneous equation, find the characteristic roots R1 equals 2, R2 equals 3, which are two distinct real roots. Write the homogeneous solution with undetermined coefficients. Y sub h of k equals c1 times 2 to the k plus c2 times 3 to the k. Step 2. Find the particular solution of the non-homogeneous equation. From the form of the input signal f of k, consult the table. Since 2 is a characteristic root, this falls under the second row of the table. Assume the particular solution has the form y sub p of k equals a times k times 2 to the k. Substitute the particular solution and the input signal into the original difference equation. When substituting, obtain y of k minus 1 by replacing every k in y sub p of k with k minus 1, and obtain y of k minus 2 by replacing every k in y sub p of k with k minus 2. Carrying out the substitution and calculation yields a constant a equals -2. Step 3. Find the complete solution of the equation. The complete solution is the sum of the homogeneous solution and the particular solution. Substituting gives the following expression. Using the initial conditions y of 0 equals 0, y of 1 equals -1, we obtain the following two equations. Solvent yields C1 equals -3, C2 equals 3. Substituting gives the complete solution of the difference equation. Now, let us think about the following. 1. If the initial conditions remain unchanged, but the input signal changes, what is the complete response y of k of the system? 2. If the input signal remains unchanged, but the initial conditions change, what is the complete response y of k of the system? It is clear that if the input signal changes, the complete response must be recomputed in full. If the initial conditions change, the complete response must also be recomputed in full. As with continuous time LTI system analysis, using the classical method to analyze the response of discrete time LTI systems has the following limitations. If the excitation term on the right-hand side of the difference equation is complicated, it is difficult to handle. If the excitation signal changes, the entire solution must be recomputed. If the initial conditions change, the entire solution must be recomputed. This method is purely mathematical and cannot highlight the physical concepts of the system response. Finally, let us summarize the steps of the classical method for solving difference equations. The complete solution of a difference equation equals the homogeneous solution plus the particular solution. 1. Find the homogeneous solution. From the characteristic equation of the homogeneous difference equation, find the characteristic roots. Determine the form of the homogeneous solution according to the three cases of characteristic roots. At this stage, the homogeneous solution contains undetermined coefficients. 2. Find the particular solution. The particular solution has the same form as the input. Substituting the particular solution and the input signal into the original difference equation allows us to solve for the undetermined coefficients of the particular solution, thereby determining the particular solution. 3. Determine the undetermined coefficients in the homogeneous solution. Using the known initial conditions of the system, substitute the general solution into these conditions to determine the undetermined coefficients in the homogeneous solution. Finally, please complete the following exercises to consolidate the content of this lesson.